So it's my pleasure to invite our next speaker, Janis.
So thank you very much, and thank you all for keeping your seats. I know I'm the last one between you and your lunch break, but I'll try to keep this interesting. What I'm about to present is kind of an intermediate snapshot of an investigation we started sometime in the middle of last year. Most of the work is actually done by my colleague Dominic and our student Philip, and well, with some minor supervision from my side, so I get to present. What is this about? Well, this is actually about what happens when the large Python community is kind of discovering HPC, and you get a whole bunch of new users with a new software stack, and what does it do to us from an HPC perspective? So I actually am a machine learning guy, so just a quick introduction. Fraunhofer is a very large nonprofit European research organization similar to US national labs. And we are the competence center for HPC within Fraunhofer. So we have a very large service division. We run HPC systems for end users, but we also do lots of research in HPC tools. Some prominent ones are distributed file system, global address space programming, and so on. I'm heading the group of large-scale machine learning. So I'm actually from machine learning. So I'm kind of the Python guy entering HPC a couple of years back, but we'll see what this does to us. So quick motivation, you've probably seen this is actually fairly old from end of 2017. Python is exploding. So this is some stats from Stack Overflow. I don't know, probably we're here right now. And this is not only triggered by the hype in machine learning and data analytics and some nice features Python provides. So you have tons of Python users, and at the same time it also does something most people do not see right away. It's kind of pushing the convergence between HPC, cloud, and big data technologies as these users that are usually used to working in cloud environments come to HPC systems and start asking questions. Why doesn't this work like it? I'm used to it. And Jan Odegaard said something about diversity when he started this conference. And this is a different kind of diversity. It's a completely different user group that has a completely different perspective on things. And they're smart guys. So sometimes it's worthwhile listening to them. And on other sides, it's there's the need to help them to get along with HPC systems. Why is Python so popular? It's just one tiny slide here. Well, I think the main cornerstones of the success of Python is at once the very low entry level. So compared to C++, you can basically start right away. Doesn't mean that you're a Python programming expert just because you can do scripting style Python. It's kind of universal programming approach. So if you're a functional programmer, you can do it. If you're object oriented, you do it. If you're just a script person and want to glue stuff together, you can do it perfectly. It has a very easy interface function to interface existing high-performance code. So we see that most stuff that look like Python are actually only Python wrapper around something that has been programmed in C++ or even Fortran. It has a huge community. We've seen that. So if I don't know how to do something in Python, I just type it into Google, and I probably end up on Stack Overflow and getting 10 perfect answers to my problem at a very abstract level. So what I can do, together with this huge amount of libraries available in Python, with very little code, I can do amazing things. And I think that's what's driving the people. You can get physics simulation, a really nice visualization, and everything with a couple lines of code. One problem that actually comes with it, that people don't care what's inside the box of that library. And this is one part of the headache that it's actually causing us. I will point out to you in a second. So why should we as HPC people actually care about the Python folks? They could go to Amazon, so what do we care? Actually, if you look at it from a perspective as running your HPC system, there's a lot of pressure. getting your funding for your new machine, you have to have these high potential users. Now the machine learning people get a lot of funding, you want to please them. If you run a university system, there are tons of users who start building their own HPC systems somewhere in their staircase because they're not satisfied with the university's HPC center service. So we see all sorts of strange things. So you should really care about. And I think the second, even more important aspect is these people come from this different background and they look at things differently, and actually they have some pretty nice ideas we might want to adopt at the end of the line. So I think it's a two-sided process here. So I split this in basically 3 parts. What are, from our perspective, what we see in daily-to-day operation, and we have a large number of Python users because we have a GPU cluster that's basically built for machine learning. So we have, I don't know, 90% of our jobs are Python jobs, some Python wrapper at least. So what are the challenges? First challenge is we have to deal with a new kind of software stack. Second one, and I call this the dark side of Python, and I will spend some time here. And the third one is the new users. I will do this real quick because I already talked about this a lot. So what are the common pitfalls of Python? You probably know this. There are basically 2 Pythons out there. There's Python 2 and Python 3. And some users don't distinguish it's just Python, but actually it's 2 different things. And you can run Python 3 with your Python 2 interpreter and the other way around. And this causes all sorts of headaches because you need all the libraries for Python 2 and for Python 3 and so on. So the community is really trying to converge and has been trying to retire Python 2 for over a decade now, and it somehow is not dying. Why? Because there are so many nice libraries out there built on Python 2, and then you need Python 2 front end if you want to use them. So the clock is ticking. The official end of support is by the end of next year. So there's not much time left. And one question you have to ask your users: hello users, do you know that, and are you aware of this, and are you ready for this? Because they will be there January 2nd, 21, and complaining it's not working anymore. So that's a real concern. The other thing is Python package management problem. So Python already came from the early start with a very nice package management system, but we usually end up with a large amount of incompatible packages. So you can have package A and B, and you can have A and C, and so how to resolve this? In the beginning, this caused a lot of headaches. And the next one is that we also have a very high demand for what I call external packages, which are kind of software packages that should be on the system to make the Python stack run. And of course, the last one is especially hard in machine learning. There's an extreme pressure in development, so we have new versions every couple of weeks. And the users always want to have the latest stuff. So this is not like the conservative HPC world where we basically take the compiler, which has been around for at least 2 years until we deploy it on the system. We always need the latest stuff, and that also causes a lot of problems. Many of these problems actually have been solved with the introduction of Anaconda. I think most people who work with Python already know Anaconda. That really made it very easy to manage packages, to have user space environments, so the user can create their own environments, install packages, and so on. And this is really, really nice. And it also kind of solves this Python 2, Python 3 problem, because you just simply have 2 different environments for Python 2 and Python 3. So everything should be nice. And usually Python users know this. And because they know this, this actually causes some trouble. Because they come on the HPC system, the first thing they do is install Anaconda in their home directory and just install the packages they want. You could say that's not a big deal, but actually full-scale Anaconda distribution takes about 5 gigabytes. And if all of your users do that, redundantly, you're spending a lot of disk space in the home directory. So you kind of don't want your users to do that. And the other thing is that they are kind of used from the desktop environment to also install non-official packages. So you got the latest paper, they made an Anaconda package. Somewhere on their private server, you can use the Anaconda mechanism to install that. So you kind of have an uncontrolled flow of software packages into your system. And these packages, I will show you in a second, can actually cause severe headaches in your system. So how to solve this? Well, actually what we do is there is a nice mechanism to actually install a global Anaconda repository which allows users to have local environments, so only the environments are in their home. And you kind of have to enforce, so basically what we do is we redirect downloads of Anaconda if they start a wget or something on the Anaconda repository. We'll tell them, I'm sorry, use it the other way. And the second thing is we fairly fastly retreated to actually starting all of the jobs in containers. So we're using Singularity, but other peoples are actually looking at different containers, just to handle all these external dependencies. So especially in machine learning, people are used to work with Ubuntu. And you get this paper with this nice code you really want to run, and it says, these 3 lines of Ubuntu install code and then the Python package, and it kind of doesn't work if you have a Red Hat-based system. So we just put everything in the Singularity container, and we allow the users to modify their containers, and then we just schedule them. And the next thing is you can also run a local Conda repository. It's called Conda channels. So whenever users are trying to install a new package, they can actually be redirected to your local repository you control. So unfortunately, containers do not solve all the problems. One of the problems we've been fighting with for a long time is that especially for deep learning, we have these dependencies on GPU drivers. And usually you have a stack like this. So TensorFlow is just an example. You have the TensorFlow network, TensorFlow framework on top. This depends on a very specific version of CUDA-DNN. If it's just off by the second digit, it won't work or will do funny things. So this really needs to match. And usually this needs to match a specific version of CUDA, which again only works with certain NVIDIA drivers. So you always have this package. Now users always want to have the latest stuff, but on the other hand, you want to have code which is only 6 months old that still should be running on the system. And this is kind of a problem because even if you use containers, the GPU driver is outside the container. So you can change that. And one of the main problems we had is that if you actually want to change the NVIDIA driver on your system, you had to reboot the system. You couldn't unload and load the driver like you could do with other kernel modules. And NVIDIA kind of saw this problem. Now with CUDA 10, they have a new mechanism. We're just experimenting with this. It looks good so far, so it's kind of getting away of this headache. So we can partially reload the driver and have different versions of the driver at the same system without rebooting, which really helps a lot. Now let me come to real headaches. We have noticed that occasionally Python jobs crash and crash hard. They take out entire nodes. And we spend a lot of time figuring out how does this happen. And here are some parts of the answers to it. We're not completely through with it, but that's kind of the direction it's going. And most of it actually comes from, and I call this the dark side of Python, design choices that have been made deep, deep inside of Python many, many years ago before anyone thought of running this in parallel on a multi-user system. And this is causing problems now. The 2 main problems, and I will show slides for them. The first one is that, and I'm talking about CPython, which is the most common version implementation of the Python standard. The CPython interpreter is inherently linear, which means it has something that's called a global interpreter lock, which means that your interpreter can only interpret 1 line of Python code at a time, and everything else has to wait. And that has some severe consequences. And the other one is Python memory management. And if you combine both on an HPC system, it can cause a lot of headaches. So let me just very briefly, and I'm totally oversimplifying this for the sake of time. Basically, what happens in a Python interpreter, you always go linear through your code. So now Python actually has a threading library, but it doesn't do what HPC people actually would expect of a threading library. So with the Python threading library, you can actually start new threads, but it doesn't happen like this, like you would expect that you have parallel execution. Because of the global lock, all the threads have to lock the global interpreter, which they share. So you only have like a execution on this thread executes one interpretation command, then this thread, and so on. So this is not, so you don't get a parallel utilization of several cores. This is not useless. You can actually use that if you want to get large I/O operations, or if you have external libraries which actually have C++ code underneath, which then start their own threading, which is independent of the Python interpreter. But you have to be aware of this, and this only hurts performance. What really hurts is what the Python guys then started to get around of it, because then people had the idea, well, if threads don't really parallelize, then just do parallel processes. So what happens in many, many Python libraries, and there's actually a toolbox for it, the Python multiprocessing toolbox, they actually basically fork child processes out of the main process. And so you start a process here, and maybe you import some library. You don't even know what it's doing because it doesn't say it in the description. And this library decides to start 20 new processes. And all of these processes may include another library that also wants to decide to start some threads or some child processes. So what you end up is a gigantic tree of children, grandchildren, and so on and so on. I recommend you just watch some of the Python applications with HTOP. It will quickly fill your screen how this is really spawning off. Now, for a single desktop user, this actually isn't a real problem. But if you do it in a multi-user environment, you end up with really, really bad problems. The first thing is that there's no resource awareness between these processes. One child process doesn't know what the others are doing. So they all try to get as many resources as they can. And some of the libraries we've looked at, they just go and grab every CPU kernel they can get, they grab all the memory they can get, and then you end up with deadlocks and tons of conflicts. So, and if you combine this with a batch system, you will even end up in the situation that these child processes are actually ignoring the limits set by your batch system. So they don't care about the number of cores you've set when you started your Slurm job. They actually oftentimes don't care what the pinning was. They just use any core they can get. Might it be owned by some other user? And you also run in really big problems terminating all of this, because usually, like the init tree is built in Linux, you cannot terminate the parent node until all of the children have been terminated. But your Slurm batch system doesn't know anything about them. It just started this process. So, and oftentimes we see lots of zombies on the system. So job terminated, and there's still some Python process running, taking up resources. So I have to speed up a bit. Actually, this is a nice chart what TensorFlow looks like, even though I told it to use only 2 cores starting the batch process. The last thing is, and I will skip over this really, really fast, is if you combine this with the memory allocation you have, the Python memory manager is really lazy, so it basically only allocates memory if needed. It's optimized for small data blocks, and it does its own garbage collection, which is, again, guided by the overall lock. So if you have some process that's taking up too much memory because it doesn't know what the other processes are doing, and you're going into swap, your garbage collector has no chance to return and clean it up because everything's locked. And then your process might die, and these zombies stay on the system, and the next user that is coming on the node has no performance at all. So how to contain this, last 30 seconds. It's not enough to run C groups, even though we highly recommend this. It's not enough to run it in containers. It even will survive the termination of the container. It doesn't break up the context, but usually it would still run. What helps actually is to start it with task set, and on top of that, we actually closely monitor what is going on a node after the user left. So basically, we have a manual cleanup, and sometimes we even have to start nodes because we can't get rid of that job before. So that's it. I already talked about the users. If I get 30 seconds. Basically, one very strong need of these users is to work interactively. So they really like to start a batch system. And how to solve this. If you're interested in how to solve the interactivity, we have a little booth in the lunch break. We have this open source tool, which basically does scheduling of containers into an HPC system with a web front end for Python users. If you're interested in that, just stop by, and I already took too much of your lunch break. Sorry for that.